Imagine a perfectly smooth, continuous curve gliding through space. It is an unbroken path. Now imagine that line suddenly begins to vibrate. It sprouts infinite jagged teeth, fracturing into a static of microscopic sharp corners. This is a classic mathematical paradox, a function that is continuous everywhere, meaning it never breaks, yet it is differentiable nowhere. How can a line be drawn without once lifting the pen, yet possess no measurable trajectory or defined slope at any point? To solve this, we look to James R. Munkres and his foundational text, Topology. Chapter 8 provides the map. Before we can build the monster, we must understand the environment it lives in, the Baire space. Baire spaces provide the rigorous machinery needed to prove that these extreme functions aren't just errors, they are a legitimate structural consequence of the rules of analysis. Standard calculus intuition suggests that if you zoom in far enough from a continuous curve, it eventually looks like a flat line. That resulting line is the tangent, giving the point a defined slope and a derivative. When dealing with advanced topological spaces, this visual assumption is a trap. If a curve is so densely packed with corners that no amount of infinite zooming ever reveals a flat segment, the derivative fails. To study such functions, we must move past geometric intuition and define what makes a space robust enough to hold them. In section 48, Munkres explains that to understand topological largeness, we must first define mathematical thinness. This is called the nowhere dense set. Formally, a set is nowhere dense if its closure has an entirely empty interior. Visually, it looks like this scattered dust on the real number line. If we take an open interval and try to place it entirely inside this set of dots, we find it always captures empty space. The dots are too sparse to fill even the smallest segment of the line. The set of integers within the vast line of real numbers is a perfect example. A nowhere dense set is essentially mathematical dust. It is so flimsy that it cannot solidly fill any subregion of our space. A Baire space is a space where every countable intersection of dense open sets is itself dense. Imagine these layers as sets full of holes. No matter how many holy layers you stack, you will never align the holes perfectly enough to empty the space. Points will always survive the intersection. Munkres states the core theorem: every complete metric space is a Baire space. This makes the real number line the ultimate example of a robust, unhollowable space. Compare this to the rational numbers. Because the rationals are just a countable union of points, they can be completely hollowed out. They do not possess the structural integrity of a Baire space. The Baire Category Theorem guarantees our complete spaces are indestructible. They cannot be exhausted by a countable sequence of nowhere dense dust. With our Baire space established, section 49 shows us how to construct a function that violates our intuition. We will build a continuous, nowhere differentiable curve through an infinite sum of smaller and smaller waves. Our base is the function h of x, representing the distance to the nearest integer. It's a simple sawtooth wave. Scaling the input by 4 multiplies the frequency of these teeth. Then, scaling the output by 1/2 shrinks the height of those spikes. We add this new, smaller, faster wave onto our base wave, creating microspikes along the original slopes. We repeat this infinitely. The frequency increases rapidly as the height of each new layer drops. Because the heights of these added waves shrink geometrically, the series passes the Weierstrass M-test. This ensures the series converges uniformly, meaning the resulting limit function inherits the continuity of its components. Because the shrinking amplitudes are mathematically bounded, the resulting curve never tears or breaks. It is perfectly continuous. Now we must prove why the derivative fails at every single point. Zoom in on any point on this fractal curve. No matter how deep we go, we find more sharp peaks. To find a derivative, we test the limit as a sequence of points gets closer to our target. We look at the slope of the secant line between these points. The math of this slope is brutal. While amplitude shrinks by half, frequency quadruples. Each new wave we add multiplies the localized slope by 2. This steepness compounds toward infinity the further down the sequence we go. The secant line oscillates wildly between extreme positive and negative angles. It cannot settle on a limit. Because every microscopic zoom reveals an even steeper corner, the derivative simply does not exist. We can now see why Munkres pairs these concepts. Baire spaces provide the framework for largeness in topology, ensuring that complete metric spaces won't crumble into dust. The pathological curve shows that continuity doesn't guarantee smoothness, it only guarantees a lack of breaks. The Baire Category Theorem reveals that these monsters aren't just rare accidents. In many complete spaces, the set of functions that are continuous but nowhere differentiable is actually dense. This categorical logic allows us to treat the entire space of continuous functions as a rigorous, structured field, even when the functions themselves defy geometric intuition. These concepts prove that true mathematical understanding demands the abstract, uncompromising framework of topology. When studying Section 49, don't just memorize the sawtooth formula. Focus on the mechanism, shrinking amplitudes to preserve continuity, and compounding slopes to eliminate the derivative. For the full rigorous proof, consult Munkres. Like and subscribe for more deep dives into the mechanics of higher-level mathematics.